Okay, hello everybody. Good morning. Am I coming in loud and clear? Let me know in the chat if you can hear me. Hello everyone. Shub, Alan, Sneha, Nandan, hello. Matthew, Abdul Rahman, Serena, Masatoma, Dijant, Eloisa, Duhang, Jovanka, Yuhao. Nathaniel, hello, good morning, everybody. Good morning. Thanks for joining us. I know it is super early in some parts of the world, like in India and other parts of Asia. So really appreciate you coming in today. Today, we're going to continue with calculus. And tomorrow, we also have a calculus lecture. So on Fridays, we change. Week 1 is algebra, week 2 is calculus, week 3 is algebra, week 4 is calculus. Okay, so you'll need your calculus notes for tomorrow. Hope you're having a good week too. Just to remind everybody, Mobius has pushed back the submission date to, I think it's Monday. So you get another chance at the week 1 assignment. Yeah, hope you're having a good day. Let's have a look at what we're going to study today. So I'll share my screen with you. And today's lecture is about 2 ideas. The first is the talking about the pinching theorem, and the second is the idea of continuity. Okay, so if you look in textbooks or on the web, the pinching theorem has different names, but it's all about taking limits. All right, so you can also talk about the sandwich theorem. Sandwich makes me hungry. There's also the squeeze theorem. Okay, so these are all the same ideas, and the purpose is to help us evaluate a limit. Now, continuity is slightly different. It's a property of functions, and continuity is a nice property because once we know a function is continuous, then we can do things with it. Okay, so this is it's a nice property of certain functions. So these are the 2 things we're going to be exploring today. Now, you would have already seen the pinching theorem in this week's Mobius tutorials. Okay, so now what we're doing is we're sort of giving you a bit more information about the pinching theorem so you can get a bit more theory and a few more examples and stuff. But people have been asking me earlier in the week, Chris, what's the pinching theorem, right? Let me just go back here. I'll just do this for effect. They go, Chris, what is the pinching theorem? We haven't seen this in lectures yet. And I'm like, well, we'll do it on Thursday. So now is the time. Now is the time. Okay. All right. So 2 ideas, that's what we're going to look at today. All right. So like I said before, the basic idea of the pinching theorem is to help us take or evaluate limits. And it's very geometrical. The pinching theorem has really nice geometric properties, although we use algebra to make it work, and inequalities. Okay, so the pinching theorem relies on inequalities, and that's the basic idea. Okay, thank you, Shub, for sharing that link. I'm just looking at the chat. So Daniel, sausage theory. Tell me about sausage theory in the chat. Okay, do you mean like a salami, something like that? I'll just put that in the chat. Salami principle. Let me know in the chat. Yeah, yeah, exactly. Just like a salami, right? So I'll show you some pictures, and then continuity is a second thing, and we'll look at some basic examples. All right, so we're going to do the pinching theorem first. So what is the pinching theorem? Well, I'm glad you asked. Okay, so I'm just going to draw a basic picture, and I'll show you some nicer pictures later. All right, suppose that you have two functions, and one function might look like this, and the other function might look like this. Okay, and one function is above the other one, but they both have the same limit. In this case, it's just some number L. Okay, now what the pinching theorem says graphically is that if you have a third function that lies between these two functions here, the green function has to have the same limit as the other two functions. Okay, so geometrically, you've got a green function in this picture that you want to take the limit of. If you can construct two other functions that squeeze that green function to the same limit, then the green function has the same limit as the other two functions. Okay. So let me show you a picture on GeoGebra, and we can work it out. All right, here is a what shall I do here? That's approaching a point. I'll tell you what, I'll come back to that later. Okay, the other picture is good enough for now. Okay, so this is where x gets, for example, x gets large and positive, where we're approaching infinity, right? All right, so here is the statement of the theorem. And there's two statements because we can either approach infinity or we can approach a finite point, okay? So here it is, you're given this, usually, okay? So the g is the given function. You've got to construct these two functions such that they have the same limit. If this is true, then the function in the middle has the same limit as the other two functions. Okay? So that's it written as a theorem, but it's really easy to show as a picture. Okay? So this is usually the given function. You've got to come up with these two functions, and your choice, you can choose these. They need to have the same limit, and that forces the function in the middle to have the same limit. Okay, and a little bit of strategy. There are many possible choices for this and this, but simple is usually the best starting point. Okay. All right, so that's the theorem. You've seen a picture. I'll do some more pictures on GeoGebra. Let's see how it works. Okay, so actually, I'll do another picture. Right. So let's say I have a function like that. Oh, h of x. Yeah, sorry, thank you. That should be h of x in there. Let me tidy that up. So just make sure there's a correction. That should be h of x. So that should be there. Okay, thank you, Aichen. Good spotting. Okay, make sure you've adjusted that. Okay, so again, the second limit So that's H, that's F, right? G's in the middle. So I think Azalea, it's okay now. Yep. Yeah, they go to the same limits. Okay. All right. So again, what you usually have, let's just do a really basic example here. Let's do something like I don't know, sine x all over x squared. That can be your given function here. Okay. And this will sort of oscillate around and do all sorts of stuff. And as x gets big and positive, it drags the function down. So we sort of know that the function is going to approach 0. Okay. What we can do with this function is compare it with two other functions. Okay. I'm going to compare it with 1 on x squared and negative 1 on x squared. So starting from a basic inequality like that, I can multiply both sides by, or everything by x, or divide by x squared. And so this would be your f function. This is your g, and this is your h, okay? So drawing a picture then, it sort of looks a bit like this, where maybe I'll draw one on my on GeoGebra. Let's see. Okay, I'm just loading something up in GeoGebra here. Okay. So if I go back to my graph here, these functions like this is like maybe your 1 on x squared. This is going to be something like your negative 1 on x squared. Both of these functions go to 0 as x gets large and positive. So they squish this function in the middle to do it too. Okay, so let me go back to my GeoGebra picture and I'll show you something that's a bit more precise. Okay, so here is the function sine x on x squared, and it oscillates around the origin. If I put in that function and that function, then you can say you see both of them squeeze that orange function down to 0 as x goes to infinity. Okay. Okay, so that is a simple example of the pinching theorem or the squeeze theorem or the sandwich theorem. Because this goes to 0 and this goes to 0, this limit as x gets large and positive must also go to 0. Okay? All right. So let's do an example and see how it works. Now, what you'll find with this is that you usually start with a simple inequality and you work with it to get back to the original function. So you can see here, I can form an inequality on sine, and then I want to get back to something like this. All right, question in the chat from Daniel. We use the pinching theorem in instances where we wouldn't be able to take the limit. Correct. Yeah, it's helpful, or it's unclear what the original limit is. Okay. So yes, it's a strategy for taking limits where we might not know how to do it otherwise. Okay. So in this case, let's call this function g of x. Okay. And what we want to do is come up with a f and a h that satisfies this the inequalities from before. So let's carefully start with an inequality like that. That's true for all x. And if I divide every side by x cubed plus 4, that's always positive, I can get the middle function to be exactly what I've got over here. Okay? And so now this is going to be your f of x. This is going to be your g of x. This is going to be your h of x. Okay? So the question now, what happens to these two functions that x gets large and positive? Well, that's going to go to 0. That's going to go to 0, and it squeezes that one to 0. Okay? So let's do that. So by the pinching theorem, now notice that I'm naming the theorem there. So that's important to do when you're doing your answers, because it shows very clearly that you know exactly what idea you are drawing on or you're referring to. Okay? Now, of course, you probably saw this and go, well, I know it's 0 because x to the 4th plus 1 drags this down and completely dominates the situation. That's fine, but this is a slightly more rigorous and detailed approach. Okay? So that's how it works when we approach infinity. What about when we approach points? Okay, so you can see over here, we're approaching infinity. Does it also work if we approach points? And the answer, let me do the big dramatic thing. Right? So the question is, will this pinching theorem still work if we approach a finite point? And the answer is yes. Okay, the answer is yes. So there's a question from Daniel. Yeah, Daniel, the strategy is sort of contained in this. Simple is usually best. Obviously you want these two things to hold. Okay, so you can't just choose any f and h. You want these two things to hold and these to hold. So the strategy, you can see here, we started with a simple inequality and we built the middle function into this just through multiplication. That's a great way to start your strategy. Now, it probably won't work every time, so you need to be a little bit more flexible with what you're doing. Okay. All right. Yes, Naya, good question. If it's x cubed instead of x to the power 4, what will we do? Well, yeah, it's as long as x is positive, you can still do this because we're approaching positive infinity, not negative infinity, right? Yeah. So there we go. So we don't have to, like, if it was x cubed or something here, it'd be fine as long as you're assuming that x is positive, because x to the 3 plus 1 is positive. So for x positive, so that's no problem. Okay, so what about points? Approaching finite points. You got it. Here we are. So now we're just approaching a finite point A. Okay, so I've got to touch this up again. This is obviously a hangover from the last one. That'll be a H. So same inequality. The only difference here is that we're approaching a point and you get the same thing. Okay, And so as a, let's just draw a little picture. Let's see if I can fit it in here. So there's a point A. And let's say this is your H function, and that is your F function. What it means is that your G function has to go through there. Okay. Right. Okay, Aidan, if a question lets me find limit by definition, is it pinching theory? No. Okay. No, I don't think so. I think what they want you to do is use the, like if you want to use, you know, epsilons and m's and things like that, it's not pinching theory. Okay, so this is not this. Okay, hope that makes sense. Okay. So inequalities, same limits, it forces the middle function to have the same limit. That's the idea. Okay, so this is like your G function in the middle. Okay, so if you know one, the other one's really easy, not a problem. All right, let's do an example. I'll put this on GeoGebra first, but this would be something like G would be this function, and let's see what happens. Okay, so I'll switch over to GeoGebra and I'll just show you something and I'll come back. All right, so here is the function and its graph. Okay, now you can see from the picture, it looks like the function is going towards 0, I guess. Okay, but let's put in two comparison functions. Okay, so the red one is x squared. The blue one is negative x squared. And you can see they both squeeze the green function down towards 0 as x approaches 0. Okay, so that is a classic example of the pictures behind the pinching theorem. Okay, yeah, it does look beautiful and above, but many students do these problems using algebra, which is fine. Okay, so let's have a look at a strategy for that, and it's similar to the previous example where we start with a simple inequality and we move towards something like this. Okay, so let me now, cosine of course is between 1 and -1. Of course, x can't be equal to 0 here, right? So this function isn't defined at x equals 0, but that's not a problem because we don't care what happens at x equals 0. We just want to know what happens as we get close to 0. Okay, so now the next strategy, I don't want that. I want x squared cosine of 1 on x. So let's multiply both sides by x squared. And because x squared is positive, we have something like this. Okay, again, we're not including x equals 0. So this would be your f of x, this would be your g of x, and that would be your h of x. Okay, so now we know the limit of this as x goes to 0, the limit of this as x goes to 0, and we can do that. So that's 0. That's also 0. And so by the pinching theorem, again, I'm using the name. You can call it sandwich theorem or squeeze theorem. We have the following. Okay, so we're pretty happy about that. Now, of course, you can plot this if you have the software, not a problem. But sometimes what you'll be asked to do is come up with these functions, okay, and write an argument that connects, the whole solution together. Okay, so start with a simple inequality, refine it to get what you want in the middle, take the limits, and then invoke the pinching theorem. And we do this a lot in mathematics. There's a complicated thing. We use simple things to try to understand the complicated thing. That's exactly. Yeah, love it. Let's have a look at Pinchy. Oh, that's so cool. You know what, Daniel? I used to say that. I used to say that in lectures a long time ago. So Michael is having fun there. Yeah, I did that too. It's so cool. Pinchy. All right. So that's when we approach a point. So the strategy so far, you can see in both cases we started with simple inequalities and tried to get the function through multiplication or division. Then invoke the pinching theorem. Okay. All right. So that's a couple of examples on the pinching theorem. You will probably have seen some of those questions on Mobius. Okay, so now hopefully you have a better understanding before Monday's deadline of what pinching theorem is and all that sort of stuff. Great. Second thing for today's lecture is continuity. Okay, so continuous functions. So let me talk about that for a bit, and we can do some examples and stuff. So the idea about continuity, it's a nice property because it helps us know that the functions and the graphs have a predictable behavior in the sense that there's no jumps in the graph. Okay, when we have a really chaotic or jumpy function, it's hard to it's harder to deal with mathematically, right? And it's harder to use in theorems and all that sort of stuff. Okay, but the thing that I like in understanding continuity is that you can draw its graph without lifting your pen off the paper. Okay, so for example, if I had the graph of, I don't know, x squared, I can draw the graph without lifting my pen off the paper. But if I have another function like this, let's say a step function, so it goes like this, I have to, okay, to draw that blue curve, I go like this, and then I have to pick my pen off the paper, place it down here, and keep drawing the graph. Okay, so this graph is continuous. This is not continuous, at least at that point, 0. Now, there is a limit definition, and this is important to know. We define a function to be continuous at a point if the limit, as we approach the point, is equal to the value of the function at the point. Okay, so there's sort of two or three things going on here. This limit has to exist. This value has to exist, and they have to be the same. Okay. It has to be the same. All right, so three things. This has to be defined, this has to exist, and the two things have to be equal. Okay, so really important. It's a very important definition. You'll use that all the time in this course when you want to check to see if a function is continuous or not at a point. If this doesn't hold, then the function's not continuous. Yeah, Abdul Rahman, let's have a look. So two ways of understanding: drawing with your pen and not lifting it off the paper, or more formally using limits. So let's have a look. All right. Now I've just, that was a x equals 1 here. I've changed it to a 2 because it's easier to deal with. All right. All right. So let's have a look at this graph. If I'm going to trace this graph out, watch what happens. Okay, I put my pen down there and I can draw all of that, and I can draw all of that, but then I have to take my pen off the paper and go down there. So x equals 4 is obviously a point of discontinuity. The function isn't continuous at x equals 4. Let's keep going. I go up there and then, oh, I have to jump. X equals 5 cannot be a continuous example. Then I have to go back down here. The rest of the curve I can just draw. So that's a very informal way of understanding continuity. But let's use this definition here. Okay. All right. So I'll keep that up here and see if we can get into that. Yes. All right. So let's have a look at the first point. Okay. Who can tell me from the graph what is the limit as x approaches 2 of our function? All right, so if we look up here, we notice that the graph from both sides is approaching 1, right? So this is 1. And what is the value of the function at x equals 2? So these two things are equal. By this definition, our graph is continuous at x equals 2. Okay. All right, I'll get to the comments in the chat a bit more. Okay. Nandan, I'll come back to your question about step functions in a minute. Okay, that's a good question. All right. All right, so that's definitely continuous. This is the formal way of showing it, and just tracing around is the informal way. All right, let's have a look at x equals 3. All right. If I, again, trace my curve, I don't have to take my pen off the paper. So it looks like it's going to be continuous, but let's formally do it. Who can tell me what is the limit as x approaches 3 of our function? Who can tell me in the chat? 0. Thank you. Shub, Ronan, Abdurrahman, Sarina, Ashwin, Yuhao. Okay, so that is definitely going to be 0. And what is the value of the function at x equals 3? 0. So we would say again, this is continuous. Okay, so the first 2 points were continuous. What about the next 2 points? Okay, x equals 4. All right. For this one, it's a little bit more difficult. So we're going to come in from the right and in from the left. Who can tell me? Let's have a look. So let's divide that up into two limits. So the left-hand limit and the right-hand limit. All right. So as we come in from the right, what is the function approaching here? Who can tell me in the chat? Yeah, Shub. That's right. So you can see coming in here, we're going down towards 1 again. And on the left, what's happening is if we come in from the left, what is the function approaching? 2, correct. Now, you can see the left-hand limit and the right-hand limit are not equal. So, the limit as x approaches 4 does not exist. So, this definition up here is broken because the left-hand side, it doesn't make sense. Okay? So this limit doesn't exist. So we would say f is not continuous at x equals 4. And informally, there's a jump in the graph. So you could say that there's, that informally that there's a jump, so it can't be continuous. Okay. All right. What about the last part of this question, x equals 5? So again, let's approach 5 from each point, each side of the point. Okay. And who can tell me, let's go here. What these two limits are. So who can tell me? It looks like it's approaching 2 from the left and 2 from the right. I think, yeah, thanks Daniel and Dijant. And who? Azalea. So it looks like 2 and 2. So the joint limit definitely exists. And who can tell me what is the value of the function at 5? What does f of 5 equal? Yeah, it equals 4. Thank you, Daniel and Serena. F of 5 equals 4. And these two things are not equal. Okay. So it breaks the definition. Even though that's defined, we don't have the equality. All right, so we can make a conclusion. F is not continuous at x equals 5. Okay. So two different kinds of continuities there, I guess, or two different situations. The left and the right-hand limits didn't exist in this case. Over here they did, and they were equal. This limit didn't exist. Over here it did, but you've still got that point that's causing a problem. Okay. Yeah, Nandan, it's an interesting question. Once broken, always broken. Here we can't fix that break, but here we can, because I can just actually redefine the function if I wanted to. Okay, so this is unfixable, but this one you can fix it. Okay, now Nandan had a good question here. Let me just go back up here for a second. Actually, I'll go there. About a function like this, which is not continuous, and he asked about some sort of application or something like this. If you study engineering, you'll see functions like this all the time. And this is like a unit step function or something like that. And you can think of it as a switch. Okay, so here the switch is on and instantaneously it gets switched off and it just jumps down there. Okay, so that's a simple example of a function that's used in, say, electrical engineering that gets switched on and off. That's discontinuous. Okay, all right. A couple more examples, and then we've finished, and algebra will take over. Let me, I'll give you a picture of this, and I can relate it back to this example. Okay, so this is giving you a split function, and they're asking you to find a value at x equals 3 for the function that makes f continuous. So how does that relate to what we just did? Well, here, there's no way of redefining the function to make it continuous at x equals 4. But here, you can redefine the value of the function to make it like a nice smooth curve, so you don't have to take your pen off the paper. Okay, so let me show you. There's a lot to take in here. Okay. All right. So let me go back here and see if I can. Oh, yeah. Okay. So the first thing you're probably looking at is going, oh, I can factorize that. Of course you can. Okay. So you can factorize the numerator, and you can end up with this simple function. Okay, so this part of the function really is just a linear function. Okay, but this thing isn't defined at x equals 3. Okay, because you can't make that cancellation if x equals 3. Okay, all right. So what we would like to do is, let me just get my notes, to consider this. This is what we want. That's the basic condition for continuity at the point x equals 3. Okay, so here f of 3 equals beta, that's some number which we want to determine, and let's take the limit as x approaches 3. So we can do it from the left. Which is pretty easy. So you just put in x equals 3. And you can do it from the right. Okay, again, very easy to do. So again, you've just put in 3 there. So both of these limits are the same. Okay. Now you probably don't have to write all of this out. It's pretty easy in this example. So we want equals 6, not 3. 6. Okay, 6. The joint value is equal to this. All right. So we want these two things to be equal, okay, in order to satisfy this. So who can tell me, what should I make the value beta equal to? Who can tell me? Yes, Steve, Shub. Who? Snea. Kai, yes, thank you. So we make beta equal to 6. Okay. So pretty easy. That's a pretty easy example. Now, if I put that into GeoGebra, for example, let me just go up there. okay, you can see here what GeoGebra has done is it's simplified it, and it looks like the function is defined at x equals 3, but if I put in t equals 3, it goes, I don't know what you mean there. The reason is because it's not defined for t equals 3. Okay. Sure. No, I think for an easy one like this, you don't have to always do it. They will get a little bit complicated. I'll show you a slightly more complicated example now. Okay. So for this next one, I would definitely do the left-hand limit and the right-hand limit. Okay. So let me share this one with you. So this is a very similar question now. The only difference is we've got some absolute value signs in the numerator. Okay. So this is a slightly more difficult question. All right. So what does this look like as a picture? Well, I am glad you asked, because I'll go back to GeoGebra and then I'll show you how to do it sort of algebraically. But we can learn just from drawing a picture, right? So this is the function here. Okay. And you can see, well, who can tell me from the picture, what is the left-hand limit as x approaches 3 from the left? Who can tell me? -6. Excellent. And if we go up here, what is the right-hand limit as we approach x equals 3? It's also 6. So the question is it possible to fill this gap? Is it possible to fill the gap and make it a continuous function at x equals 3? That's correct. It's absolutely impossible. Okay. Yes, Colleen, I agree. Menglu, it is impossible. So that's what it looks like visually. Let's have a quick look algebraically, right? And the idea is just to simplify the absolute value. Okay, so what you can do is you can say, all right, that's going to be x squared minus 9. And what you can do is you can just flip it over. Okay, so the green is now that. Okay, so you know it's going to change sign between -3 and +3. And so you can write it out like this. So between -3 and 3, it's going to look something like that. Okay. For everywhere else, it's just going to be this. And at x equals 3, it'll be that. So you can simplify that. You're going to get something like this. You're going to get that. -3. And you're going to get that. Okay. So if you take the limit, the left-hand limit, because we're interested in 3 here, right? So you want to take the right-hand limit, the left-hand limit, and you're going to get 2 different answers here, just like we saw in the graph. So when x is bigger than 3, this is it. And when x is less than 3, you're going to be in here. So you're coming in from this side. So this is going to give you -6. And you can see, well, unfortunately, these things are not equal. Okay, so the limit cannot exist. And what that means is our continuity condition cannot hold. Why? Because we can't have equality because this thing actually doesn't even exist when a equals 3. Oops, sorry, let me do that again. Don't worry, that wasn't an earthquake in Melbourne. If anyone's in Australia, did anybody feel the earthquake? There was a big earthquake in Melbourne. Some people in Sydney said they felt it. Okay. So this limit doesn't exist, thus no value. Hi, Bill. Will ensure continuity. Oh, don't worry. It's not always possible, though. It's not always possible. So we can't plug the gap, right? We can't plug the gap. So let me just quickly go back to my, right? You can see here in the picture with GeoGebra, it's not possible to plug this gap with one point. It's just impossible, okay? So let me go back here and we will finish up. Yeah, so there it is. So with that one, Shub, getting back to your question, I think it is really important in a question like this to check the right hand and the left hand limits. But when it's super simple, I don't see why you need to do it. All right. So Daniel, is this just saying that for a function, we can't give you the exact value, but if both left hand and right hand limits exist, then we can get you as close as you like to the beta. You can even do better than that. Like you can actually make it precise, right? So if you look at this discontinuous point, you can really redefine or move that point and plug that hole. Okay, and that way you can then draw the curve without lifting your pen off the paper. And in the other example, like this one, it's impossible because the jump is too great. The jump is too great. Okay, so that's it, folks. My daughter, I've got a couple of children here. My daughter's 10. She said, "Dad, you've got very boofy hair today." Yeah, I haven't been to a barber or a haircut in about 3 months because everything's closed. How are you managing your hair? Mine's out of control at the moment. All right, Daniel, can we do that because the limits of both sides converge? Yeah, well, they both equal each other. They both equal each other. So that if they don't equal each other, then the bigger limit doesn't exist. Okay. Yeah, Jordan, maybe I should do that. Maybe I should just cut everything off. Although I'd be worried it wouldn't grow back. Yeah. All right. I'll hand over to Bill if there's questions or you want some extra clarification. Now is the time. Oh, beard trimmer. Have enough. Good idea. Yeah, mine's crazy. Sometimes I'll it just gets out of control. Thanks for a wonderful lecture, and I will see you tomorrow. There's a calculus lecture tomorrow, but just have a break. Enjoy Captain Bill and algebra. And if there's any more questions, put them on the chat, or I'll just turn on the where are we? See if I can set up the sessions. If anybody wants to chat, then I've just turned on the audio. Okay. All right. Thank you, Alan, Nathaniel, Snea, Vina, Bailey. Break. Take a break. Take a break. Don't forget to keep working through Mobius. Okay. And remember, you have an extra few days to submit the first assignment in case you want to. All right. I will see you later. Oh, Anubhav, I think Mobius has been pushed back till Monday for the first assignment. I think that's it. But if you already submitted it, well, probably doesn't really matter. Okay. All right, folks.